Laplacian equation. So first, we need to, because we are going to talk about the forward theory first about existence. So it is necessary for us to review a little bit about linear theory, okay, existence. So in the linear equation case, the main equation we're being concerned is this one. That's the initial boundary problems. Okay, and however, for some special cases, we also need to consider having inhomogeneous type. Okay, now this is a very special case. Actually, this whole theory can be extended to the general second-order equations. So I will maybe mention a little bit later. Here, in order not to introduce too many symbols, we'll just take this one as the case. Okay. So here, the principal part is Laplacian, so there's no coefficient involved. So the coefficient basically involved in the first order term, and actually there's no constant term involved, but you can add one. Okay. But so let me state the general theory for this equation first, then try to extend a little bit about the other case. Okay. So here we're assuming the following. So B is in C of omega bar, and the F is in C to omega bar. So those are the Holder space, and also the little f is in C to alpha. Okay, so that's the summing of this coefficient. So this initial value problem. So in this case, and there's a couple of things you can talk about. First is maximum. Well, I mean the maximum principle is obvious for this case. We don't have to think about it. So in this case, the main thing is about existence and uniqueness of solution. So this means that in this case, under these assumptions, so they exist. So this implies that there exists a unique solution U is in C to alpha omega bar. That's unique solution set for this condition. Okay. And you actually in the beginning of this semester, we talk about the equation like this. Maybe assuming f is 0. Okay. I talk about the existence, the proof of existence.
Yeah.
Do you still remember anything about that?
Which solution you just use? Lax mirror.
Yeah?
Lax mirror. Lax mirror. Relax mirror.
Lax mirror.
Yeah.
Zero.
You can get
It's only applied to
the weak solution.
yeah. I mean, it's a weak solution.
Yeah.
So here we talk about the
But
whole
one,
space solution.
Oh.
Yeah.
You talk about I know if I pronounce it wrong, so the Perron method or potential theory.
Oh, okay. So potential theory is for the Laplacian
yeah.
operator, right?
Yeah.
So the thing is here is the general case. I mean, the whole method applied to the general second order liquid equations. So there is it's a passage from
The method
Laplacian
of continuity.
continuity method.
Yeah.
Right?
Yeah.
So what we need in order to use continuity method is basically a zero in function analysis. It's not PDE, right? But you have to do enough PDE in order to apply that function analysis to get what you want, right?
Yes.
Right? Now, what is the things we need before we apply this continuity method?
Uniqueness.
No, uniqueness traditionally follow from maximum principle. This will follow. I mean, satisfy maximum principle.
Close. Let's see.
That's the central part of the electric theory. It's called a priori estimate,
Oh, right.
Holder estimate, right?
Yeah,
So this estimate is that, I mean, suppose I don't know anything about the existing solution. However, I know that if solution exists, then that solution should satisfy certain estimate. That's the priority estimate, right? So, so this estimate is like this. The C2 alpha on the bar is less equal to C times. Now here, because I involve two terms, so I'm just write down the result. In this general setting, little f C2 alpha omega here. And plus the capital F C2 alpha. Sorry. The alpha is, the F is C alpha. C alpha. Well, if F is a C2 alpha, then you can increase the, when you load the solution,
Yeah.
if the coefficient is of the source. Okay. Here is C alpha on the top. So first, this is called a priority estimate. So this estimate is proven before we establish existing solutions. But the here, the C, the constant C is important. C is actually involves something omega and the dimensions and the B, C alpha omega. Okay. Which depends on this. Now, if the equation is more complicated, there's never involve other conditions. Okay. So then now using this priority estimate, this estimate, okay, then you can combine this with the method of continuity. The method of continuity is basically you consider a relation between the Laplace. So let's call this as the L U. Okay. So you make a connection between Laplace and LU. So like P plus 1 minus T L. So you make a connection between these operators, and so that's why the LT is equal to this. Okay. So LT is considered is a map from the C2 alpha omega bar to C alpha omega bar. So this is the different operator. Apply to any function here, you get that, right? Okay. And the maximum principle shows that this map has to be okay, sorry, no. Yeah. Because previously, now suppose F, well here you have two data, the capital F and little f, okay? Now if you, the little f choose to be 0, okay, then you can make this connection go directly, right? But however, if the little f is not equal to 0, you have to first, you have to transform this problem, so let's call this problem. Okay. Into the problem, the Laplace plus dx f u on the boundary is equal to 0. So you remove the f. Okay. So the way to transform this is very simple. So you can pick a phi, basically. And if C2 alpha with the B on the boundary is equal to beta f. You can choose phi first, okay? So there are a lot of choices for the phi. Then you can transform into this equation with or cos with a different f, right? With a different f. And this f will still be in the C alpha omega bar. So therefore, we only need to consider this equation. If we can prove the existence of this equation, then you will get the existence of this equation of plus. Okay? So then you can see, then you can just consider this using the method of continuity applied to this operation. And the thing is, this is going to be obviously more objective. And the a priori estimate here is able to show that the U C to alpha omega is basically some constant C. And uniform constant C is the LP applied to the U CR. So this in some sense this shows that if inverse exists, then this means that the norm of the inverse is uniform bounded. So using these conditions, then using this method, we can show that if this operator is surjective when t is 0, when t is 1, for instance, then this operator is also surjective in the other end. So this gives you the existence. Okay. So the linear theory basically is followed by the method of continuity. And method of continuity is basically is followed by what? Contraction principle. Yeah, contraction principle. Okay. So this is I'm trying to review a little about this linear theory, because when we treat the positive equation, we have to use this estimate a lot of times. Okay. All right. So the equation here, we're going to the new we will look at this. Okay, so this is the positive equations. In this equation, we are going to assume certain conditions on the coefficient. So cos the f is going to still be e to alpha on log here on the boundary. So here, in all the discussions, we assume the omega itself is a bounded domain with smooth boundary, Okay. So here, there's a nonlinear the quasi-linear coefficient involved here. So this coefficient should satisfy certain what we call structure condition. So we're assuming that this A, you see here, in this case, what is A? So in the linear case, the A, the corresponding A is what? So assuming P is the components involving the gradient U depends on n variable. Okay. So AXP is equal to what? If you think about the linear case, the XP is just equals to the BX and P, right? Yeah. It's just like this. So it's a linear function of P. And here, you can see that this is a nonlinear function of P. Now, of course, you can see that any A written like that, no matter what kind of B involved here, it takes the derivative. I mean, it's differentiable in P, right? Okay, so here it's naturally, we have to also assume that A is kind of differentiable. Okay. Now here, what we really need is AXP is in the C1 alpha. So here the B is just alpha, right? Okay. But you think about P is, in the P variable, it should also be differentiable. So 1 alpha. Okay. Now this condition is not the best condition. Okay, but for the simplicity, let's just assume that. So this will be omega cross Rn. Okay, so that's one of the conditions. Another condition is that Ax0 is equal to 0. Now this condition actually is also necessary because think about this linear case, P sitting here, so if I P to 0, everything is 0. So this condition basically will guarantee the uniqueness. It will guarantee uniqueness of solutions. Okay. Another condition is growth condition. the growth condition is that we take the quotation xp. Okay? And this should be less or equal than in some constant mu times 1 plus the p squared. So this this estimate should hold uniform x variable, but in p variable, it's allowed this function to grow in the quadratic form. And in the linear case, it's only linear. This is the linear growth, but here it's allowed to be quadratic growth. Okay, so these are called a structure condition. Then under this structure condition, we'll expect that this problem has a unique solution. Okay, there is a unique solution. So the question is whether this implies that there exists unique U belongs to C to alpha. But this is true, and we're going to prove it. Okay, so this is the forward theory we want to establish first. Okay. So the theory for this equation will be very similar. I mean, the proof is different, but however, the final form will be very similar to that. We are going to get a uniqueness and existence solution, and also we are going to get a Shorter estimates. Okay, the final form will very similar. Okay. Now, in order to do that, you look at the linear theory, and I skipped one of the things here. It's actually the maximum principle, right? The maximum principle. But maximum principle, we learned this before. I mean, this is not a big deal. The main thing is the existence. And the existence is based on what? Based on the priori estimate. Okay, so we're going to establish both for all for a positive linear case. So I'm going to give a complete treatment of the maximum principle in this positive linear case. But for the priori estimate, I can only give you the result because there's no way you can go through this proof in this class. Just like in the linear case, we are able to go through that. Okay, so first is the maximum principle. Now, maximum principle say that if U is, now it's not necessary to assume U is a C2 alpha. Now, the reason we want the alpha involved, I mean, the reason we want to consider the whole space is because the elliptic theory, the existence theory requires the whole space. For the uniqueness, it's not necessary. Okay, so assuming this is a C2 solution. Okay, so then is a solution. Okay, so then we will imply that the U on the boundary excuse me, the maximum or the minimum is controlled by the F on the boundary. So that's called maximum principle. Okay. Well, a correct way to, more accurate way to say this is the maximum and minimum principle. Okay. It's written in one form. But that's all we need. That's all we need. Okay, so I know that for the linear case, this is true, right? So the case is how do I reduce this to the positive linear case? But there's a trick. The trick is because you have the structure condition, this condition involved. Okay. Now suppose you have a solution like this. Suppose you have a solution. Okay, so I'm going to take a look at this equation. Oh, look at this quantity. Okay. So this quantity, in some sense, can be written in a different way. So I'm going to write like this: 0 from 1, d dt, then a x t gradient u. I can write this way because I know the I know one, I know the fundamental theorem of calculus, right? I mean, differentiate and integrate, be careful. But however, this is supposed to be, obviously this should be equal ex with t equal 1, greater than u, minus a x t equals 0. When t equals 0, so this becomes 0. But I know that ax 0 is assumed to be 0. So with this structure condition, then this coefficient basically can be written like this. But this one, if you differentiate that, if you differentiate the t, you're using the chain rule, right? You using chain rule, this becomes AP x and t greater than u. Then what's next? You differentiate in t variable, then you still have the gradient, right? So gradient will be outside. So so the gradient itself is independent of t. Now moving is outside of the integration sign. So this is what we use. Okay? So I'm going to call this is called the distance. And distance is called the bx dx greater than u. Okay? So this can be defined. It's a function of x, right? And also it has something to do with the gradient. It's entry for the gradient. So I write this expression, this integration as dx. So I don't care about this integration, but integration itself is not important. But the important thing is I treat this as a function of x and gradient u. Something like this. Now because of this, you can see that once this is being satisfied, then it's will satisfy this way. Laplace u plus the b x greater than u and greater than u. Like this. Okay? Now you can see that this is similar to the linear equation, right? Because although this guy depends on greater than u, but for what? This is a function of x. So if you have a solution, then the solution can be written like this. It takes the linear form, right? And the only thing I need to check is what is the regularity of this guy. Okay, so B is involved AP, right? Now what is the regularity with AP? So look at the structure condition. A is in C1 alpha. So AP is in what? C alpha. And here, the gradient gradient is U is in what, C2, right? So gradient U C1. So C alpha combined with, I know C alpha combined with C alpha will get you still C alpha, right? So here you can see that C1, so therefore it's basically it's C alpha. So as a function of x, it is C alpha. Okay. So now you can, if I apply the linear, apply the linear maximum principle, and then you're going to get this linear, because this guy no constant involved. Okay, only the boundary value and the solution set. Okay. So that's the first result for this partial linear equation that's a maximum principle. And this maximum principle will be important later, even though it's very simple. The main thing is it's play two roles. One thing is that it's going to it's going to give you the uniqueness immediately. Solution has to be unique, right? Because if you have when f equals 0, you are obviously get exactly equal 0 immediately, right? Okay, so so that's the first one. We are going to use later. So now let's move on with the next thing we want is the priori estimate. So whenever to prove that, but I'm going to state it without. another way is called, so this is also called a gradient estimate, the whole gradient estimate, okay? So this estimate is, I'm going to state is the weeks performed, okay? So assuming you, it's just CT through. For this appliance. Okay, so of course on the boundary is satisfied F, and this one is, let's say it's yeah. It's only C2 volume now. Okay. Okay, so I'll just take any solution which is C2, okay, from this equation. The thing is we're going to establish, I mean, if you think about the L infinite law, then the maximum principle will be this estimate, right? But here we're going to talk about the first order law, that's the gradient. Okay, so this means that it exists a beta. Okay, a beta is between the 0 and 1. So this beta actually depends on the coefficient A. Depends on the equation. And a constant C. Now C will depends on a couple of things like omega, like a dimension, and also this may involve the law of A. Okay, so